Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.
Our next speaker is Pascal Vincent. He flew away all the way from University of Montreal here. Pascal had many contributions to deep learning. He's probably mostly known for denoising autoencoders, which shed some light on the importance of injecting noise during training. And today is going to tell us how to compute efficient exact gradients when in training deep networks when the target space is very large.
Thank you. So this is joint work with my students, Alexandre de Brébisson and Xavier Boutillier. So first for motivation, nowadays we tend to try and learn neural networks that have very, very large output spaces. And the first time I actually encountered this problem was back in 2000 when I was working with Yoshio Benjo on neural language models that at the time exotic idea. At the time we already had the problem of having to predict a large output vocabulary. We were dealing with like 30,000 words for vocabulary. It was already a computational problem then, and now it is still a computational problem because you want to predict the probabilities of those very large vocabulary, those very large number of classes, which, with a learned representation of a reasonable size, gives you a very expensive O of a big D times small d computation, for example, at that output layer. So that's by no means restricted to neural language models. The problem has now known also as extreme classification, and there's even a workshop at NIPS about this, and has a lot of application. It arises in many cases. It also arises in memory networks and the like, where you have softmax over the size of the memory, which can become quite large. So that's for the motivation. The currently employed approaches basically fall in two categories: either changing the probability model, like imposing a hierarchical structure with a hierarchical softmax, or sampling a small subset of those many output dimensions at each time, which we see in noise contrastive estimation or important sampling-based approaches. But relative to computing the full output, both these approaches are very crude approximations. So what I'm going to talk about, I'm going to show that it's possible to do the full exact gradient, so no sampling, no nothing, in O of small d square, so the dimension of the representation, not of the output, rather than O of big D small d. But with a caveat, that's going to be for a restricted family of loss functions. Okay. So what we'll have our inputs that are our input vector to the network, as well as our target represented as sparse vectors. Now, sparse vectors, they can live in a very large space. This big D is going to be big, size of vocabulary, but with a few elements that are on. So all we need to do to represent them is to keep those elements indexes and values. And what this buys us is when we have to do matrix multiplication with such a sparse vector, well, it's simply going to be a weighted sum of a few columns, actually k columns of that matrix. So we're going to have an operation in O of kd instead of O of dd, where k is very small, whereas big D is very, very big. Okay? And similarly, when we want to do a rank 1 update of such a matrix with a sparse vector, well, actually, we're only going to touch a small number of rows or columns of the matrix. Okay. So again, O of kd instead of O of big D small d. Okay, so here's the kind of architecture that we're considering. We have some input, x, and some target, y, both represented as sparse vectors. These could be the vocabulary and bag of word representation or similarly. And the dimensions that we're considering here is a big D that can be huge, and a small k, the number of non-zero elements. Okay. And then we have a network with reasonably sized intermediate layers of size small d. And finally, an output layer that is the same size as our sparse target vector. But the output typically will not be sparse. So finally, these are compared with a loss. That's what's being optimized. Here I'm considering square loss. I'll relax that a little bit later, but for now it's going to be square loss. Okay? So simply comparing our output O to our target vector Y. Okay. Now if we look at the forward propagation, what we have here is a first weight matrix. That's a big D times small d matrix. Remember, big D is large, so that's a huge matrix. And that's going to take us to this layer. So normally that would be an O of big D, small d computation, a very big one. But since our input vector is sparse, this is O of kd, so it's really cheap. Okay? All the others are pretty reasonable, small d square, small d square. And now we're getting to our output layer matrix. Again, it's a big D times small d matrix. We want to go from a small d dimensional layer to a big D dimensional output. But here, there's no reason for this to be sparse, and even if it was, this wouldn't help us much, because really the big dimension here is this big D dimension. So we're going to have to take to multiply with all the elements in that matrix. So that's a O of big D, small d, prohibitively expensive operation in many cases. I'm showing this to contrast what's happening here in the input layer, the sparse input, versus the output with a sparse target. Okay. Then this output is compared to the target, sparse target, and this gives us the loss. Now let's look at the backpropagation. We want to do a gradient backpropagation. So we compute here the residual. That can be O of D, big D. Well, it can be a little cheaper, but. And here comes the expensive part. The update to this weight matrix is a rank 1 update, but it's a rank 1 update to the full big D times small d matrix, right? So it's also O of big D times small d. And computing the gradient with respect to H is also a big D times small d operation, because that's a matrix product with a full matrix and a non-sparse vector. Right. But once we have this gradient, then all the rest, so all this is prohibitively expensive. All the rest is pretty cheap. This is all simply O of D square. Same for the updates of these D by D matrices. And once we get that input, back to that input, updating this big D times small d matrix is cheap, because it's a rank 1 update with this sparse input vector. Okay? So contrary to what happens here for updating the output matrix, updating here the input matrix is very cheap. Right. But altogether, this is a big D times small d operation with big D huge. Okay? Actually, I'm using a little bit of the notation. It's 3 big D times small d, which are these 3 operations here. So we're going to concentrate on what's going on here at that output layer. All right, so we can do much better than that. What I'm going to show is that it's possible to compute the loss, L, the gradient with respect to the last hidden layer, and perform the exact same gradient update to that full matrix, big D by small d matrix. All is possible in O of small d squared, okay, without ever computing the full output. Okay. And how do we do that? So there's 2 tricks. The first trick is that we're going to keep an up-to-date small d times small d matrix Q, okay, which is defined here. And then we can compute L cheaply. So if we look at the computation of the loss, initially it's WH minus Y. So this is our output. Okay. This is a big D times small d computation. Okay. But if we can rewrite it this way and develop it, and then here we see we have a W transpose W. We can replace that by our matrix Q, which is a d times d matrix, small d times small d, so it's a small d square operation. And similar here, we have a W transpose Y, but Y is a sparse vector, so this is an order of K small d operation. Okay? And this is cheap also. So you see what we've done here is we've replaced this very expensive big D times small d operation by these operations that are all small d square. And we can compute the loss without ever computing the output. Similarly, for computing the gradient with respect to h, which we need to further do the backpropagation, we can play the same trick. So here we have a W transpose W that appears. That's again Q, and again all this is O of small d square without the need of computing the output WH. All right? So that's the first trick. Now, if we look at our update of W, so the normal gradient update of W is really a rank 1 update of W, which is non-sparse. So we have this rank 1 update here. We have H vector, which is small d size, and WH minus Y, which is our residual, which is non-sparse, okay, and this big D size. So this is actually going to modify to touch all big D times small d elements of W. Okay? So there's no choice, it's O of big D times small d. Okay? So note that we can rewrite that by developing this in this manner. And by developing it in this manner, we see that it can actually be decomposed in 2 sequential steps. First doing this, then doing that. Okay, we haven't changed anything here, and the complexity is still always big D times small d. So how are we going to do to modify this W using only small d square operations? So the trick is to represent this W implicitly. We're going to represent this as the following factorization: product of a V matrix, which has the same dimensions, and a small d times small d U matrix. And then, instead of updating W, we're going to update it implicitly by updating V and U. And so we take the 2 previous steps. So this first update to W is equivalent to updating U in this manner, and the second update to W is equivalent to updating V in this manner. So here we had a full update of W that's of big D times small d. And here we have simply a rank 1 update of U, which is a small d times small d matrix, so that's cheap. Here, provided we keep an inverse of U up to date, that's also cheap, small d square. And the big gain is really here, is because now, here we had a full update of V, which was not sparse, so it touched all big D times small d elements. Here we're going to have a sparse update of V, which is only going to touch K rows of our V here, okay, instead of touching all big D rows. So big D can be 800,000, and K can be 2 or 3. Okay. So note that this is not the same as doing ordinary backprop on U and then V. Okay. So it's very different. It does, however, do the exact same update as the normal backprop update of a single matrix W. Okay. There's some bookkeeping operations. We need to keep up to date U and Q. They're also all D square, so skipping that. So that gives us a full 9-step algorithm that's altogether O of small d squared. Okay. So what are the benefits of this approach? Well, first, there's a big computational benefits that we expect. We have replaced basically an operation that was 3 big D times small d operations, elementary operations, by roughly 12 small d square operations. So that's an expected speedup of big D divided by 4 small d. So if we take sizes, for example, a sparse target size of 800,000 with a reasonably sized dimension for the presentation of 500, the speedup is going to be 400. Okay. And the big gain here is in memory access, is we're only accessing K small d elements of V rather than the big D times small d elements of W. So this can be straightforwardly extended to the mini-batch case. It doesn't change the complexity. Also, the approach that I showed for squared error is applicable to the spherical loss family, which is basically any loss that can be expressed by using only the output elements that are associated to non-zero target elements, and Q, which is the sum of square of the output elements, okay? And S, which is the sum of the elements, optionally. So the linear output plus squared error that we've just looked at is part of that family, and unfortunately, regular log softmax is not. But there are other normalized losses, like the linear spherical softmax, where we use a squaring instead of an exponential. Okay. So regarding the measured timing, so we did two implementations of this, one on CPUs, and one on CPUs and one on GPUs. So this is comparing the timings with the unfactorized, so the normal standard backprop, and our factorized version. So if you look at the standard backprop for mini-batch here of 128 examples, and for, say, so this is a log scale. Okay, so it's almost nearly half a second for a mini-batch of size 128. If we use GPUs instead, it's almost 10 times faster. But what's remarkable here is if you look at our algorithm, which are in green, you see that their timing for that mini-batch is independent of the vocabulary size. Right? That's what predicted. So, so that's nice. And here are the speedup curves. So in red is where our big D divided by 4 small d, which is our theoretical speedup. And the measured speedup with our implementations on CPU is in blue, and on GPU is in green. Okay, so it's pretty close. And if we look at the overall speedup, so that's comparing to a naive version. So the CPU unfactorized naive version. If we look at the output layer only, if we use the GPUs instead, it's like 6.8 times faster. If we use our CPU factorized version, it's 700 times faster than the CPU unfactorized. And if we use the GPU factorized, it's 3,000 times faster than the CPU unfactorized. And that's just for the output layer computation, so forward propagation, backpropagation, and update. And it's similar for the whole model speedup. A little less, of course, because there's the other layers that are taking some time. Okay, but it's still a big speedup. All right. Note that we also put here the hierarchical softmax, just for reference. All of them not optimizing the same cost. But except for that hierarchical softmax, all these versions compute the exact same cost and gradient update. It's just different algorithmic versions. Okay. So to conclude my talk, I showed an approach that yields a huge speedup and that allows to perform the exact gradient update in networks with a very large sparse targets. The timing is independent of output size, and the gain is from fundamental algorithmic complexity improvement and not from hardware-specific optimization of the tricks. So the main limitation of the approach is that it's restricted to losses in the spherical family. In the future, we want to investigate the spherical loss versus the softmax, compare those. Actually, this has been done to some extent, and so far it's not as good as for language models. And we're looking for compelling applications. This approach might be better suited to sparse regression targets, actually. Okay. Thank you very much.
So while we're taking questions, if you're a spotlight presenter, please approach and line up here, prepare for your talk. And if you have questions, please approach. There are 2 mics. There's a question there.
Your trick that you're using at the output layer is in some ways very reminiscent of the kernel trick that's used to transform, say, SVMs from primal to dual representation. Do you want to comment on that? Because then, you know, in theory, you could do infinite dimensional D, or is that possible? Big D.
Right. So I have given it only little thought so far. I noticed also that it's indeed reminiscent of the kernels, but I don't think you could do infinite dimensional, because the whole trick is to actually compute this big output matrix W explicitly. And you don't have that, because what you have basically when you have a kernel is you have a kind of predetermined fixed expansion, right? So it's definitely similar. I don't think it could be applied for infinite dimensional.
Okay.
From what I thought.
So we're a bit short of time, so we'll stop here. Thank you.
Each year, Microsoft Research hosts hundreds of influential speakers from around the world, including leading scientists, renowned experts in technology, book authors, and leading academics, and makes videos of these lectures freely available.